So last time we were talking about heavy quark effective theory, and we phrased several motivations for talking about heavy quark effective theory related to things that we hadn't seen in effective theory yet. We also said that our discussion here is more general than just talking about heavy quarks. Heavy quarks is our example, but we're really thinking about having some very heavy source. So you can think of it as either a heavy particle that you want to leave in the theory. So let me rewind. We talked about heavy particles already, and what we did is we integrated them out. We got rid of them. But what if you have a heavy particle and you actually want to study it? That's related to this discussion. That's one way that this is important. If you have a heavy particle that you want to study at low energies, or you could just have a source, a static source of some quantum number, in this case color, and this would be the right way of thinking about it. So those are kind of some of the motivations, and then there was also some more technical motivations of things that we wanted to see with this theory. So we started by saying it's a top-down approach, so we should be able to just take QCD and take the limit and expand. But it's a little more tricky than it was so far with like light quark masses for Kyle perturbation theory, because the mass is in the numerator and we want to take the limit that it goes to infinity. Okay, so we put a question mark beside this equation, and we started instead thinking about expanding the propagator. So if we write the propagator out for a heavy quark, you've got mass terms in the numerator and the denominator. And when you expand it out, after using the equation of motion and expanding with P equals mq v plus k, so we introduced a vector v. V squared was 1. And then we introduced some fluctuations, k. So there's m's hiding in this p as well as that p. The quadratic term in the denominator cancels. There's a linear term that survives. There's linear terms in the numerator. The linear terms give, once I just look at what they give this first contribution. And then there's some higher order terms, and we drop them. OK, so for the propagator, we had no problem taking the heavy quark limit, and we got out this expression. We also then thought about the vertex, just a gluon coupling to a quark, heavy quark. And if this is the result in QCD, this 1 plus v slash over 2 is a projector. What that means, if you square it, you get back the same thing. And we said, well, if there's two propagators on either side of this thing, I can think about it putting a projector on either side of this thing, and that gives you this result with just a v mu. OK, so the Feynman rule for this guy can be simplified by using the fact that on either side of it are sitting these projectors. And if you take those two facts into account, we can actually encode them in a Lagrangian. We could just write it down. Say we want a Lagrangian that gives that propagator, lowest order propagator, and that lowest order vertex. And that's what this is. So the v dot d has in it a v dot a. V dot a is giving this guy. So that's the v dot a inside there. And then 1 over v dot k, that's the v dot partial. Right? So I v dot d is I v dot partial. I don't know which sign I'm using here, but I think it's the minus sign. Using plus? No, using minus. I'll switch throughout the course. In each chapter, I'll use a different sign convention to keep you on your toes. In this chapter, I will stick with this sign convention, since the source that we're using for the reading is using this sign convention. OK, so this is the v dot a, and this is the v dot k that we have over there. Now, I've encoded, the way I encoded the projection relation is I said, let's work in terms of a 4-component field. So our field QV still has 4 components, but it satisfies this relation. And that actually projects it down onto 2 components, and we'll talk more about what the physics of this is in a minute. This is very convenient when talking about heavy quarks, because you often want to couple heavy quarks to light quarks. And if the light quarks are 4-component spinors, it's easy to couple them to the heavy quarks if you have heavy quark fields, which are 4-component spinors. So you could work in terms of a 2-component Lagrangian that doesn't have this projection relation. But for technical reasons, it's better to work in terms of the 4-component one. Makes things simpler. So that's, in some sense, an indirect derivation of the leading order HQET Lagrangian. Is there any questions about that?
What if you you don't have a propagator on the other side?
What if I don't have the propagator on the other side? Yeah, so we'll talk about the spinors in a minute, but it's the same story for the spinors. That they have a projection relation, which is exactly the same projection relation. So whether it's a line sticking out or whether it's attached to something else, it's the same. OK, so let's now go and derive the same thing directly. And the trick we're going to do is the following. We need to cancel out this m in the numerator. And the place that m hides is in the p in this formula here. So if we think about some field that's fluctuating in space-time, we can pull out from that field the analog of that big piece, p, if we pull out a phase factor that looks like that. So let me just write this. So far, this is just some redefinition of these objects on the right-hand side. And I'm setting up two objects here because I'm going to break the field into these two pieces that obey different projection relations. OK, so if I sum these two up, the v slashes cancel, qv plus. These are just two components of I just split it by two orthogonal projectors into two pieces. And I've pulled out this piece here. And the reason that I pulled out this piece here is the analog of what I did here with the p, where I divided it into a big piece and a small piece. This is going to take care of pulling out that big piece. OK, so if we want to take the limit here in this equation, so far we've written out what the q's will be. We also have to write out what the d slash is. So it's convenient to do the following with the d slash. Break it into two pieces. A piece along v and a piece orthogonal to v. So the definition here of d transverse is that it's d minus the piece along v. So if you like, that v dot d transverse is 0. That's what I mean. With these relations up here, there's also another way of writing them that I should write down as well, which is a little simpler. If I rearrange these formulas, I can also write it as v slash on qv is qv, and v slash on bv is minus bv. So there's a 1 on this side, and if I combine it with the half and put things together, that's what I get. OK, so let's put those things together into here, and then we'll be able to figure out if we can take the limit. And the crucial thing, really, for being able to take the limit is to pull out this phase, and we'll talk about what physically is happening there in a minute, once we've done the algebra. OK, so just plugging those pieces together, we have that. Pull the phase through. So pull this negative phase through these terms. With this v dot d, when it hits the v dot x, we get some extra contribution. And I can group it together with this mq term, because what it does is it brings down an mq. The d transverse gives no derivative, no contribution when it hits that phase because of this relation. So pulling the phase through, the only term we pick up is this minus 1 here. And I just grouped it together. Sorry. The only term we pick up is this v slash here. That comes from this v dot d hitting that term. All right, so now put these pieces together, multiply things out, and use the fact that I've divided up the field into these two pieces that have different, I know how v slash acts on them, so I can get rid of all the v slashes by just using the formula. When v slash minus 1 acts on qv, I get 0. Okay, so for that term, for the term that has two qv's, I just have the v slash v dot d. You can also prove that when you have the qv and the qv bar, that this term actually is 0. And to prove that, you basically use the projection relation and the fact that if I have 1 plus v slash over 2 d transverse, that can be written as d transverse 1 minus v slash over 2. Again, using this formula and the fact that gamma matrices anti-commute. And then 1 minus v slash over 2 kills qv. And so a term like this one between these fields is absent, and the only term with two qv's is that one. Likewise, with BVs, it's the same story. I don't get a d transverse term. But here the MQ term does survive, and it doubles. So the v slash gives another minus 1, so there's two MQs sitting there. And then there's the transverse terms, and they come in the cross terms. So QV, BV, if I have this, then this projection relation won't get rid of it, because if I have a 1 plus v slash over 2 on the right, it becomes the correct projector for the other field on the left, and then vice versa. Okay, so there's 4 terms here, and we've simplified things as much as we can. So now let's think about what these fields are describing. In particular, let's think about what would happen if we only had external QV fields. So if we consider only external QV fields, then we can think about what happens as MQ goes to infinity. And if you have a term, so as m goes to infinity, nothing happens to this term. We have to figure out what happens to those terms over there. But this guy here, it's clear what happens. We get a field that has a mass, mq, and that particles are just getting heavier and heavier, and they're decoupling. When you get particles that get heavy, they decouple. So BV decouples in this limit. So diagrammatically, you can think about it like this. You have a QV. It could switch into a BV with one of these d slash vertices, and then back to a QV. And this would give some kind of diagram from this Lagrangian, which has external QV fields. But the BV field has a 1 over m type propagator. And so this goes like 1 over m, and hence goes to 0. And that's one way of talking about decoupling, that intermediate particles of that type are giving diagrams that are suppressed by 1 over m. OK, so, and you see here sitting right here, you see our Lagrangian that we want, which is the QV IV dot D BV. So if we just threw away the BV fields, we would get the Lagrangian that we want. So physically, what's going on with these two fields is that QV corresponds to the particles. Okay, we have a heavy quark. It's got particles that are of that mass and that flavor that are heavy, and it has antiparticles too. QV corresponds to the particles, and BV corresponds to the antiparticles. of this flavor. And by making the phase redefinition that we did, we chose to focus on-shell fluctuations that are close to the particles. If we'd chosen the opposite phase, plus I, then we could expand about the antiparticles, and things would have worked out in the opposite way. So I'll come back to that a little bit more